All right, hello class, and welcome to lecture 10, part C. So we're going to wrap up our discussion of Lambert's problem by giving a relatively straightforward algorithm which works in certain circumstances. It certainly is pretty effective at finding the first arc of the solution to Lambert's problem. It's not going to work so well with multi-revolution orbits, and it's not going to work very well with hyperbolic orbits, which we don't even cover in this course. So keep in mind when we go through this that it's going to work, but there are limitations. You're not going to find it's not going to work as well for very long duration transfers. It's more for the targeting problem than anything else. All right, so that's given the limitations, let's sort of define what the problem is or recall what the problem is. So the problem is I'm given the delta t and I want to find the A, which is buried here, 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 and here. Now, because I don't have a good sort of analytic expression for the right-hand side of this in terms of A, right? It's given would be given in terms of sort of these arc cosine functions, which would be difficult to combine with Newton's method, which requires us to be able to differentiate the right-hand side of the function. Now, I'm not going to say that it's impossible to apply Newton's method to Lambert's equation, because I've seen some recent papers which do that. However, I'm skeptical that it's going to work very well in many cases, and we're not going to really cover it. Another approach is to approximate the right-hand side with a series expansion, and then perhaps use Newton's algorithm to solve for it, or to find an expression for A specifically in terms of a series expansion on T. And this is actually an approach taken in several textbooks. And I believe when these problems were initially being solved, I believe Gauss used some kind of series expansion to solve for Lambert's equation. But anyway, we're not going to do that, and we're not going to use Newton. We're going to use good old reliable bisection algorithms. So bisection algorithms work fairly well when you're searching for the solution to monotonic functions, and you don't have an explicit expression for the function. You have it sort of, you can evaluate it at various points, but you don't have sort of an analytic expression for it, which is the case here because there's a dependence on A to alpha and then alpha to the right-hand side. And so that's difficult to differentiate. So again, it works well on monotonic functions. It doesn't work at all if the function is not monotonic. And that's going to require us to restrict ourselves to certain arcs of the solution. Remember, this is delta t as a function of A. So specifically, we're going to have to determine a priori if we're on the upper arc or the lower arc of this curve. So specifically, we're going to focus on the lower arc in this analysis, but the approach can definitely be reversed to find the upper arc. We focus on the lower arc because those are short duration transfers. Generally speaking, you want to get somewhere, you want to get there relatively fast, and so it makes sense to find the shortest arc. Of course, if your desired transfer is not on the short arc, you can apply the methods for a longer arc, but you have to reverse some of the steps, and I'll mention that when we get to the actual algorithm. So again, limitations of this approach inherent in the algorithm. So I'm just going to grab this figure here because I'm going to use it later on. Copy clipboard. So again, if we look at the bisection algorithm, we're going to have to restrict ourselves to this arc, which means we're going to need to figure out if we're on the arc, right? So in particular, there's going to be we're going to have to make sure that our delta t lies in this relatively narrow band here of delta t's, right? So delta t max and delta t min. And then, of course, if your delta t is greater than the delta t max, you're going to have to switch over to the other arc over here. Well, these are the same arc technically, but the other side of the arc, let's call it. So we're going to assume that we're on the bottom arc and give a method for verifying that we're on the bottom arc, and then the method that we propose is guaranteed to work. So let's consider the bisection algorithm. Here, I'll just put this over here and make it small so we can have it for reference. So the statement of the problem is we have a function, right, which is given here, g of a, and we want to find a solution to that g of a equals a given delta t. We want to find a such that these two are equal. So what's our approach? Well, so the approach is basically based on guessing. So specifically, you choose a initial range of a's, which you hope that your solution will lie in. So specifically, remember, we're trying to find a. So we're going to limit ourselves to a particular arc right here, and we have an a min here. Remember, that's the minimum energy orbit. We don't really have an A max. Because remember, this arc can go all the way out to infinity for the parabolic orbit. And so we can't technically have an A max, but we can just choose one relatively large. So in particular, we're going to choose our A max to be, I don't think it doesn't say here, but I believe we choose, I typically choose 2s to be A max. And then, so the first step, if you choose it, when you've chosen your A max, is to determine the time of flight and determine if it's short enough, right? So, and then TOF, right? And if TOF is shorter, is longer than your desired delta t, then you have to increase your A max to say 4s or something like that. Right? So just increase your max until your time of flight is somewhere in your desired range of a's. So that's the setup for the problem. So in that case, we've got this range of a's here, where we know the solution is going to lie. And so that's sort of this picture here. This is A and this is delta t. A max, say this is A min. And the next step is an iteration, which takes a while to converge, admittedly, and is basically based on guessing. So the first step in this iteration, so you've chosen these things, right? So that's sort of the setup of the problem. The second step, or the first part of the recursion, is to choose a guess for A max and A min. So since you know nothing more than the max and min values, and presumably you don't know much about the function itself, we're just going to guess the middle point between those 2 points. Right, so this is A max plus A min divided by 2. Right, that's our first guess. And then you determine the corresponding time of flight by just plugging that number in to your equation. You get a delta t1, let's call it. So now let's call it A1, right? Or AI, for example, AI. So now if your corresponding time of flight for that AI is greater than your desired time of flight, then you know that, so in that case, let's see, we've guessed here, right? So we find the corresponding time of flight. So let's say we're searching for a time of, sorry, that was a very very bad screen. So say you find that's your A1. Suppose that you calculate the corresponding time of flight, and it's say you're looking for 20 seconds or 20 minutes, and the corresponding time of flight is say 30 minutes. Right? That means that you are to the left of the correct value. It's your desired point. So because that means your time of flight is above where it needs to be. So it means you're to the left. So that means that the correct value is somewhere between this point and your maximum value, A max. So in that case, you have a new minimum, right? You have a new minimum value of A, and it's the AI, A min. Conversely, if your corresponding AI has a time of flight shorter than your desired time of flight, you know that the time of flight, the correct value of A is to the left. I think I said that correctly before, hopefully. And so now this AI becomes your A max. Right? So if your AI, your calculated time of flight is less than your delta t, you reset your maximum, the upper bound on your interval, to that value of A. And if it's greater than, you set the minimum value. Right? So in this way, you've now, in this case, this is you found that your delta t is where you're looking for this point. So you found that in this case, you found that your delta t is less than your desired delta t. Right? And so now this point becomes your A max for the next iteration. And then you repeat, you now have a interval of possible guesses, which is half as large as it was before. And so you repeat the process, you just guess a new value of A. Which is halfway between those two bounds. And you test that. Now in this case, my calculated delta t is larger than the desired value. And so now this is my new A min. Okay. And so now my interval of guesses is 1/4 of what it used to be. And I repeat the process, I guess another one. And I guess there, and it's too large, right? And so now this is my A min again. And I find a new point right here. It's too low. The dt is too low, so that's my A max, right? And I keep repeating this process until I achieve a desired level of accuracy. Okay. So this method, right? Well, very crude, is guaranteed to converge ultimately if the function is monotonic, and well, there's a solution basically. And if the function is monotonic, there will be a solution. Right? So a step that's guaranteed to converge, but of course it's much slower than the case of, say, Newton's algorithm. In particular, the error is on the order of 1/2 to the k, right? Because it's dividing by, it cuts down the interval by a factor of 2 at each iteration, which is much slower than Newton's algorithm does. So if you want, like, say, 6 decimal places, obviously you've got to increase your number of iterations. So you should not expect to be able to get an accurate answer using 3 or 4 iterations, as we did in the case of Newton's algorithm. But again, very easy to implement, and of course, utterly ill-suited to doing problems by hand because of the number of possible iterations. Again, caveats to this, we're considering only elliptic orbits now at this point. There are solutions for hyperbolic orbits, and in fact there's a unified approach to Lambert's equation for that case. So no, that's just hyperbolic, parabolic. And so obviously the first step if you're applying this is to make sure that there exists an elliptic transfer before you begin. So that's going to correspond to your minimum value of delta t. Okay. So now let's go back to that plot again. Again, I told you we're going to bring it back a couple times. Right. And just calculate those values to make sure that we are on the desired arc and to get bounds on our A min and our A max. Right. So specifically, we have a T max here to make sure we're on the right arc, and we have a T min here corresponding to a parabolic orbit, meaning a T min means you can't get a transfer between these 2 points if your time is less than the time corresponding to a parabolic transfer. So we have a nice explicit formula for the case of a parabolic transfer, which I won't get into where that comes from. But specifically, you just want to calculate this delta Tp here, which would correspond to a parabolic orbit where A goes to infinity. So that's this number right here, Tp. So make sure delta t is greater than the transfer corresponding to a parabolic orbit. If it's not, you're on the hyperbolic case and not covered in these lectures. So otherwise you need a hyperbolic transfer. Right. So that's the max. Is there an A corresponding to that? No, right? The A corresponding to them is at infinity, right? Corresponding to that delta Tp. So when you calculate this number, if delta T is approximately equal to delta Tp, that should tell you that your initial guess for A max should be large. How large? I can't tell you. Just guess a value and calculate the corresponding delta T, and if it's not sufficiently short, then you have to increase your max. So that's the first part, first step. Next is a little bit easier, or a little bit follows more directly from the earlier parts of this lecture, which is finding this point right here. And remember that we have an explicit expression for what this A min is, right? Below which, right, there's no transfer at all. Right, that corresponds to the case where those circles don't intersect, where they just intersect at a point at A min. That case. So if you may remember, we had an explicit expression for A min in that case, right? It's A min equals C plus R1 plus R2 divided by 4. Which is, of course, equal to the semi-perimeter divided by 2. So calculate your A min, and then see what the delta T is corresponding to that, right? Find the corresponding delta T, and that's your max. So if delta T is greater than your T max, then you're actually on the other arc of the solution to Kepler's problem. And if that's the case, then you've got to sort of reverse these steps. So if we go back here, in the case of on the upper arc, we reverse this, right? So A max equals A, and A min equals A in this step, right? Because we're going the opposite direction. So if delta t is greater than, we're at the max, and if delta t is less than, we're at the A. We have a new A min, right? So it reverses those steps. Another. Give me my picture back. There we go. Right. Hopefully, however, you've chosen your delta t sufficiently short because it's an intercept problem that you're on the lower arc. And if not, right, you should really get there faster. So why don't you just choose a smaller delta t if you're doing targeting? Of course, if you're doing orbit identification, right, we have a different question, different problem. Right, so again, right, this is just Lambert's equation. So it's calculated from alpha max, alpha beta max, which is a very old form of VHS, which is a very old form of video recording. So the beta max and alpha max are calculated, of course, from the standard formula. So again, got to calculate those two numbers. Alpha max is going to, A min is going to give you your minimum energy, right? Is from the minimum energy, so that's your A min on your interval for bisection. So if you've done this correctly now, then you're on the correct arc. Your bisection algorithm is guaranteed to converge, albeit not quickly. And finally, that gives you your corresponding, right, A. So you can go from delta t to A. So okay, you've got your A. Now what do you do with it? How does that determine the rest of your orbit? And so now you've got all the pieces necessary to determine your orbit. You've got R1 vector, R2 vector. And fortunately, the calculations for the rest of the orbital elements are relatively easy and not necessary. Because if you're only interested in velocity, there's a much simpler expression for the velocity at these 2 points, V1 and V2, directly in terms of R1, R2, and A. So we don't even need to calculate the rest of the orbital elements. We can just get them directly. And so that's given by the formula here. So specifically, we know we're on this orbital plane, so we know our velocity vectors are also in the orbital plane. And so they have to be some combination of the directions of these two R1s and R2s. Right? So what we just do is we normalize R1 and R2 to get unit vectors. So these are just normalized R1 and R2. And we now have an explicit expression for the velocities in terms of those two normalized position vectors. And specifically, the coefficients for those two, right? Well, actually, we actually don't use we have a third one, which just makes our calculations easier, which is the normalized version of the relative position vector. So we have UC as well. We just use that because it makes our life easier. So we can now express the velocities at time 1 and time 2 in terms of coefficients and these unit vectors. So in particular, the coefficients at time 1 are a combination of the unit vector at 1 and this UC. And the coefficients are actually quite simple, just B plus A, B minus A, where A and B are given by these values right here, where these alphas, remember, are the same ones in Lambert's equation. for the value of A that you obtained. So that gives you the velocity vectors at both time 1 and time 2. In particular, the velocity vector at time 1 is, of course, slightly more valuable because that's going to give you your delta t, which we'll talk about on the next slide. But a very convenient, very closed form solution for the velocities at those 2 points. And of course, if you want the orbital elements of this transfer orbit, now you have R1 and V1, and so you can get the orbital elements. Likewise, of course, you have R1, R2 and V2. So if you want to determine the three-dimensional orbital elements, or R2, V2, although that will give you a different F, true anomaly. So, okay, basically now we've solved Lambert's problem in a somewhat modern format. Again, right, for longer delta t's, the problem gets a little bit trickier, and you have to check the reverse directions. These, by the way, give you the prograde solutions. And of course, if you want the retrograde solutions, what do? Just negative v, right? If you're going in this direction of the orbit, v, right? If you're want to go the other direction, you just negative v, right? That's all there is to it. So at this point, we can sort of consider the Lambert's problem solved. We found a way to calculate the velocity vector at our transfer orbit. To now calculate our delta v, we just subtract the needed velocity from our actual velocity, and that gives us the vector of delta v's, and in three-dimensional space, of course, not necessarily in the initial orbital plane. And we can get from point A to point B. Now just here's an illustration of this two, I don't know why I made it so small, two non-coplanar orbits. We're trying to get from point A to point B. And here's our transfer ellipse, whose orbital plane lies in neither orbit. Right? So that's, you see the transfer there. It's fairly efficient. If it turns out to be inefficient, you may want to shorten or elongate your delta t's, depending on, I mean, this one looks pretty efficient because you're getting sort of, looks almost parallel to velocity vectors here and here. So you might need to play around with your arrival times in order to get minimize those delta v's. But again, topic not covered in this course because it's complicated. All right, so now we're pretty much done, and so we'll just sort of wrap up with a numerical example. Again, a targeting problem. I don't know, what geopolitics are going on at the current moment in time, but in this weird world, Brazil has developed a nuclear weapons program, and somehow Thailand has annoyed them for some reason. I don't know, maybe the curry was too hot. Let me tell you, Thai curry, pretty hot. And in revenge, Brazil decides they're going to launch an ICBM. It looks like it's coming out of Brasilia over here. That's the capital, Brazil. And so we, being America Global Police or whatever, decide this is unacceptable. You're not allowed to nuke Thailand for some reason. Well, I mean, obviously lots of reasons, because we like spicy curry. Yes, don't nuke Thailand. And so we've decided we have this this ICBM interceptor already in orbit. Here it is. This is our interceptor in its orbit. Fortunately for us, maybe we have multiple interceptors in orbit, but fortunately for us, our interceptor happens to be in a conveniently located position to stop Brazil from blowing up Thailand. In particular, this is the interceptor here. And Unfortunately, however, it seems like we didn't notice this in time, or we took a while to like determine the orbital path of this planet, this trajectory, or we were trying to negotiate with Brazil to like stop. But anyway, it took a while, and this ICBM is almost at Thailand, so not much time left. Fortunately, the Brazilians, I don't know what they were trying to do. They were maybe like trying to avoid Africa or something like that. But they launched it in a fairly ineffective orbit, right? They launched it fairly high up. I don't know why. Maybe they're trying to avoid radar. Who knows? Trying to avoid our interceptors. In any case, they've launched it into a relatively high orbit. So we have a bit of time left. We have to intercept during this arc. And we've the geniuses over here in interceptor land have calculated how much time we have. In particular, they calculated that it's the ICBM is going to re-enter the atmosphere in 30 minutes. Right. After that, it's going to, once the ICBM enters the atmosphere, it's going to be really hard to shoot it down because like turbulence and going to disturb our calculations and air drag and all that stuff. So we want to shoot it out before it gets into the atmosphere. So, okay, there's our problem. So we've got, we have the problem here. Here's our initial position, which we need. It's something in low Earth orbit. Initial velocity vector, which we don't have to worry about too much. And we've tracked the missile here. We've measured its position and velocity, or we measured its position at 2 points. Who knows? In any case, here we've measured the position and velocity of the missile, and we've determined, based on the resulting orbital elements. Well, actually, all we need is AE to determine the delta T at RP equals 6378. Plus, say, 500, and I forget what it is 30 minutes. Right. So we're almost set up for Lambert's problem. Right. So in particular, we've got to actually find the location of the target at the impact point. So this is R2. Right. And so how do we do that? Well, we calculate the orbital elements, right? A, E, omega, I, omega, F. We calculate what F will be in 30 minutes, right? By propagating mean anomaly, calculating F2. And then, of course, this requires solving Kepler's equation. And then, based on that, calculating the position vector at that point, R2. And that's this point right here. So these are all plotted, by the way, using some of the little code snippets that Dave Villado puts out. All right, so here's our Lambert problem. It's set up. We've got R1, which was on the previous slide. Maybe I should grab it. There's R1. We've got R2, which is that all on the previous slide too. Actually, it's not on the previous slide. Is it anywhere? Unfortunately, it's not. I didn't bother to write it down on the slide, so sorry about that. In any case, so we've got R1. Presumably, we've got R2 as well. So actually R2 occurs 12,000, so we were really high above the atmosphere. I'm not sure why we chose that one. Maybe we're just playing it safe. We want to make sure that like we get that ICBM before it gets anywhere near Thailand. In any case, so we found R1, we find the value of R2. We can now calculate those geometric parameters, right? Particularly the chord length. We find the difference between these vectors and normalize it. So the chord length is 7,000 kilometers. We find the semi-perimeter, right? That's just the chord length plus R2 plus R1 divided by 2. So the semi-perimeter is 13,000 kilometers. So now we're ready to initialize our bisection algorithm. So before we do that, we need to find those A mins and A maxes, right? So we can calculate A min. It's easy. That's S over 2. Well, I'll get to that in next slide. We also need to figure out if we have enough time to get there. So specifically, we want to calculate the time corresponding to a parabolic transfer. Figure out if we can get there on an elliptic path. So we plug these numbers into the function for the parabolic time. And we find that the parabolic time, if we had a parabolic transfer, that would correspond to 18.2 minutes. And so since we have 30 minutes, we're safe. We don't need to do anything fancy. Maybe if we were farther away, or interceptor was farther away from the target, we would need a hyperbolic orbit, but we don't. We actually have plenty of time. Next, as I mentioned, we have to calculate the minimum, A min. That's S over 2. Right. So 6,586 kilometers. And if we plug that into the Lambert's equation, we find a corresponding T max. Remember, the arc that we're looking for on Lambert's function looks like this, right? Right. So there's an arc there. We're looking at this part of the arc. Right. So T max, right, is there. And A min is here. Yeah. So we have our A min. We also have to choose an A max to initialize our bisection algorithm. We're fairly safe. We don't have to choose an A to be too large because we have plenty of time, right? Our T min is not very close to the amount of our delta T. And so we can choose A max pretty conservatively. We can choose, I'm going to choose, I think, 2S. I forget what I chose on the next slide. Yes, I chose A max for 2S. And that's just, I needed to check that, right? So I should just plug that into, yeah, I should plug that into delta T. And presumably it's something like maybe I'm just guessing here 22 minutes or something. No, that's not right. It's probably around 25 minutes. Sorry, no wait, no. It's probably around 20 minutes, I would guess. So anyway, it's larger than we need. So that's the important part. So now I just start my bisectioning. Right, so I've got my A max and A min. This one, the A min, do I have the number on the slide? Oops, wrong way. Yeah, it's 6586. And our S, what parameter did we get for S? Was 7,000, so this is going to be 14,000, our initial guess. Okay. So we average those two, and apparently it's 8,000. That doesn't sound right, but so maybe I chose something less than that. So our initial guess is 8,000 kilometers. We calculate the corresponding delta T, and it's 21 minutes, which is too fast. Right. So in particular, we need to slow down. So we're going to decrease our alpha max, right? Or high. L corresponds to min, and H corresponds to max. So high and low. So we reset our max to be this number A1, and we recalculate. The next iteration gives an A of 7,400. Again, too fast. Okay. So we have a new value of our A max, right? It's now for our max. It goes down there, that goes down there. The min hasn't changed yet, so we're still there. So we've set our new max to be that, and we've got our new A. Find our new delta t. It's 26, still too fast. So we keep going, too fast, too fast, too fast. At about iteration, I don't know, 40 or 50 or something like that, we finally get a value of A of 6,744 kilometers, and that has a corresponding time of flight of 29.99 minutes. And so we figured, hey, that's pretty good. We can do a little course correction at the last minute or something like that. So we'll keep that value of A. So our A here is 6,744 kilometers out of our bisection, with far too many steps here to list on one slide. So now we just plug these into the equations for velocity. Right. So that goes in here. We can just reuse the value of betas and alphas which we collected from the last iteration. And we get our coefficients A and B. We now calculate the normalized, oh, by the way, here I can get a value of R2, right? So we can actually, if we wanted R2, we can multiply that by the constant R2 to get the vector R2, just curiosity, because I didn't put it on the slide, just if you want to double check it. So anyway, we've got U1, we got U2, got UC, of course, right? Remember, that's R2 minus R1 divided by R2 minus R1 norm. Right? And we plug those numbers into in particular, the number for V1. So that goes there, that goes there and there, lots of arcs here. And then our value of U1 goes here, and our value of UC goes here. And so we plug those numbers in, and we get a V at T1 of, on the transfer, not the target, of 3.4, etc., kilometers per second. Now remember, we had our initial velocity from slide well before. We had our initial velocity right there. And so we plug that number here into there, and then we calculate the difference. And the vector value of the delta V we need is this, which looks like around a total impulse of about 6 kilometers per second to get to our destination in time to save Thailand. So congratulations, we saved Thailand. Incidentally, here's just the plot, right? Here's our initial interceptor. Here's the target, and here is our trajectory. You see curving around and intercepting the target. And a little explosion there where we do the interception. Yeah, always reminds me of the Star Wars 4-1, depending on how you where you're plotting the Death Star, right? And why did they need to go do a trench run, right? I mean, if they could solve Lambert's problem, they could have just like dropped their bomb at the I mean, they had like, right, the target location, right? That's R2, and they had their initial position of the spacecraft. So they could have just like solved Lambert's problem and like calculated the intercept trajectory and didn't have to go to the trench at all. They could have launched their warheads from like really high up. But no, I guess that's not as cool. But anyway, so saving the world through Lambert's problem, or heading to Mars through Lambert's problem, or Jupiter, or all these multi-planet trajectories. or just determining the orbital path of something you observe in space or space junk or whatever. Lots of applications for Lambert's problem. Lambert's problem is probably the most important orbital mechanics problem of the 20th century, later half of the 20th century. Hohmann was in the first half, so we'll consider the second half of the 20th century, at least for spaceflight. Any case, we are now done with the problem of calculating navigation paths in space. So we've covered the general problem of transfers. We covered Hohmann's, the Hohmann trajectory. We've covered bielliptics, which incidentally, bielliptics have never actually been used. Anyway, and perhaps the most important problem that we've, way of calculating transfers, Lambert's problem. The next, in lecture 11, we will digress and talk a little bit about how to generate the delta V needed for these problems and illustrate why delta V is such a scarce resource in space and why you need to build such big rockets in order to get where you need to go. But that is a topic for the next lecture. And so at this point, I will close out and wish you adieu.